Yeah, all right. And I still have the chat available if you need to ask questions. You're also, of course, welcome to just interrupt me or wave your hands around or what have you, just like always. All right, so I've got our week 4 intro to statistics, our tutorial pulled up. And I think this might have the fewest typos of all of our R tutorials, which is going to be extremely helpful for you, I'm sure. In this tutorial at the beginning, before I teach you anything, I, as always, give you a couple of links. So one is to learn more about the theory of a t-test, more information on the theory of t-tests, and then the t-test kind of grounds the ANOVA, but the ANOVA or the analysis of variance, I give you a couple of links for how to do those, including advanced ways to do them. And then I do include another tutorial on how to do cool color making stuff with ggSci, just so you can remember that. And then I do always remind you that the best way to learn is to Google it. I had a couple of students reach out to me this week and say, like, R's been really hard. I've been really struggling. I've been helping, you've been helping, but Google has been helping. And is that okay? And yeah, Google is your best friend in an R situation. You just type R, how do I do the thing? And then hopefully somebody on the internet knows how to do it. Works every time eventually. All right, so today's learning objectives. We're gonna learn the theory behind the t-test and the ANOVA, the analysis of variance. We're gonna understand the limitations of each, and then we're gonna learn how to do each one of those things, okay? Most of the time, we're gonna be talking about theory. And I'm probably gonna skip a couple things for the sake of time. But if you decide you don't know enough statistical theory and you really wanna know, you know who to talk to. Okay, as always, when we start with R, we want to do a couple of things. And I know that you already know, but I'm gonna go over it again. We're gonna go into our R document and we're gonna make an R Markdown file or an R script, whichever one you like the best. I'm gonna use R Markdown just because that's what y'all have been using mostly. Delete all that. Remember, when you're running code in R Markdown, typey is just typing. You actually need to insert a code chunk, right? So stuff I type here won't run. But if I have an R script open, every line is code, okay? So in an R Markdown document, the only thing that is code is inside of my gray box. All right, so the first thing we want to do is check our working directory. So we'll do get WD. That's the wrong function. It's just get WD. Make sure we're in our right place. We are. So great. If we wanted to set our working directory, we could do that like this, as you are familiar with. And then now that we've got our working directory, we want to hit the library and load up our BFF tidyverse. And this week, we're also going to need a few other options. I'm going to load in vegan. And you can just copy and paste this stuff from the tutorial if you'd like. And then I'm going to load in some other stuff. So we know what tidyverse and vegan do. We know ggSci, cool colors. We know patchwork, mini graphs, same page. And then we also need the performance package and the R statics package. The performance package allows us to test all of our assumptions of our statistical analysis. And the R statics package is just a simple outlier test. If you are using R on your own individual device instead of on rstudio.bodin, you probably will need to install these packages. The performance package is a time and effort saver. I really strongly recommend its use. It's very useful and very easy. Okay, we've loaded our packages and we are ready to do the next thing. Load packages. Remember, commenting your code is how you can thank past you for being smart, so you don't forget what's going on. Future you will appreciate that. All right, step 2. Let's talk about a t-test. I'm gonna show you a bunch of stuff in the tutorial because it does show us kind of what happens when you hit these functions. If you want to copy and paste each of these functions into your own R, that is totally okay with me. So we're going to be using the dataset mtcars, which, as you'll remember, is just built into R. We can just type mtcars, and there it is. So A t-test or a student's t-test is about the most basic statistical practice you could ever employ. It is used for what? Does anybody know what a t-test is for?
To measure significant difference between two data sets or two like data points.
Yeah, great, perfect. It is to assess a difference between two groups. So we're considering the mean of those groups, and really we're testing to see if those means are different. A t-test considers the mean and the distribution of points within a set of data. So that's basically all a t-test does. Notably, it only works if you have two things. If I want to compare one thing to one other thing, I can. That is all you can do with a t-test. So if you have 4 groups, you can't do a t-test because it can only compare 2 things. Okay, t-test theory. When you're running a t-test, there are some assumptions that have to be met. And if they're not met, sometimes you can't run a t-test. Those assumptions are, number 1, that the 2 distributions we're looking at have to be normally distributed. What is a normal distribution? Does anybody know what that is? What does it look like?
A bell curve?
Yeah, a parabola or a bell curve. So like this. I could use the whiteboard function on the screen, but I find that this is a little bit faster. There's your normal distribution, right? Where your mean is that point in the middle. Yeah, that's pretty much it. So we assume that our data are normally distributed, and if they're not, that can mess with our t-test. Number 2, we're assuming that the variance of our groups are equal. So what that means is if I have 2 groups and I show you a mean and error bars, is the variance of my 2 groups in that plot equal? Hopefully you're saying no because the error bars are different sizes, even though it's very blurry. Yeah, so it's making some assumptions that are like never true. Very rarely do we look at data and say, oh yeah, the error bars are the same size. And oh yeah, everything's normally distributed. Those are like perfect situations. So the t-test is a bit limited in that regard. That said, you can actually transform your data to make those things true. And sometimes those assumptions don't actually have to be met. And this is like classic science, right? We have these rules, but they're really more like guidelines, right? So basically we're pirates is what I'm trying to say. So when you're assessing normality, you can actually test your data to see if it's normal. So I'm going to show you how to do that. We do something called a Shapiro-Wilk test. And I'm going to run this and show you how it works. So I want to know, if I'm running my Shapiro-Wilk test, if the miles per gallon column in my MT-CARS dataset is normally distributed. Is MPG normal? I run my Shapiro test, and I will get this little confusing table out, and it'll tell me you ran a Shapiro-Wilks test. We found a p-value of 0.1229. So let's talk about what a p-value means. A p-value tells us whether there's a significant difference between 2 things, okay? If a p-value is lower than 0.05, that tells us that there is a significant difference between 2 things, or that there is a significant effect. And that's how a p-value works for every test. So what that really means, essentially, is that based on the statistical test that we've done, if a p-value is less than 0.05, we can be 95% confident. 100 minus 95 is 5, and that's 0.05, right? We can be 95% confident that there's a significant effect of the thing and that it's not due to random chance. That's what a p-value means. I'm never going to ask you to tell me what a p-value means, but I think it's important when you present p-values to know like what they're actually saying. When there's a significant p-value, it's telling you that some effect is significant and that we can be like 95 or more % sure that that thing is significant and that it's not random chance causing it, right? So something is driving an effect. That's what a p-value means. Okay, so we ran our Shapiro-Wilk test, MT-CARS versus miles per gallon. And before I can explain what happens with this p-value, we need to talk about another concept, and that is the null hypothesis. Does anybody know what a null hypothesis is? Yeah, Coleman, I see your hand.
Pretty sure it's just like assuming nothing will happen going into it.
That's right. So for statistics, basically what we're always assuming is that nothing will happen. The null hypothesis is the basic idea behind all statistics. So with the Shapiro-Wilk test, we're saying, is miles per gallon normal? Our null hypothesis is that it is. That everything is normal. That's our assumption, right? So we're testing that assumption. Everything is normal is our assumption, which basically means that the null hypothesis is that everything is normal, or that nothing is different than normal. If we get a significant p-value in our Shapiro-Wilk test, that tells us that that thing is in fact not normal. So you can see that my Shapiro-Wilk test for miles per gallon is 0.112, not significant. So that's normal. That's great. If I test the cylinder column, however, the distribution gives me a p-value much lower than 0.05. That's 6 times 10 to the minus 6, so 0.0000006. That's much lower than 0.05. So that tells me that the cylinder column is not normally distributed, which could be problematic for my t-test. I can do that with other things inside of MT-cars, and I can do this with any column I want, and I can see what's going on, and that's great. So that's one way to assess normality. Importantly, when you're running a statistical test, assumptions being met or not is entirely a judgment call. I can run a statistical test and confirm whether my assumption's being met if I want, but really, like, that's not that important. It's a judgment call. You can say, I'm fine, I'm just going to keep on going. And if somebody gives you a hard time about it, you can try to explain why you did what you did. Yes, Andrew.
In this example, when you say so empty cars, the Shapiro test for the cycle, so it has a very small p-value. In that case, like, what are you comparing? I guess is my question. Like,
sure.
What...
So yeah, so the Shapiro-Wilk test is saying it's comparing the data to a normal distribution. So the spread of the data, or the distribution of my data, it's comparing to like this parabola.
Okay.
And it's saying, is my data different than this normal distribution? And if the p-value is significant or lower than 0.05, then it is in fact different.
Okay.
Yeah, that's all it is. And again, this is just one way to test an assumption. We like to look at our tests for assumptions just to see how valid our statistical tests are. So you can do a normality test with a Shapiro-Wilk test like I showed you, or you can make a histogram like this one, and you can look for normality with your eyes. This requires slightly more coding, but is a lot easier to understand, right? We look at MT cars miles per gallon and we say, that's close enough to normal for me to be happy. We look at cylinder and we go, oh, well, that's not right. Something about that isn't right. That doesn't look the way I want. If we look at horsepower, that's close enough. There's a little bit of skew, but it's close enough, right? Weight, close enough. This one is the only one that looks really bad. So we might wonder about our t-test if we're comparing between cylinder values, if we're considering cylinder to be a numerical value. Okay. The second assumption is, if we go back to the top, the variance of the two groups must be equal. And I'm going to show you how to figure that out later. I'm going to show you a much easier way to assess all of these assumptions in a couple of minutes. I just wanted to show you that you can, in fact, test for them. Okay. So the big takeaway here is, how often have you run a statistical test? Maybe never, but I can tell you that everybody runs t-tests and ANOVA, and nobody checks their assumptions. I just taught you how, and I taught you the theory behind why you do it. But now I'm telling you, like, nobody cares. And here's why. Can we just ignore either of these assumptions? And the answer to that question is, we can actively ignore both assumptions as long as we have sufficiently large sample size. And that's in quotes, because what does that even mean? It's pretty much entirely a judgment call. For me, a sufficiently large sample size is that there have to be at least 5 points in every one of our averages. So there has to be 5 points in every distribution. As long as we have an N of 5 in each of our groups, we're chilling. And in ecology, it's pretty hard to have lower than an N of 5 because we collect a lot of data, right? There are exceptions to that rule, but essentially, as long as we have enough samples, we don't have to worry about our assumptions. If you want to read more on that, I gave you a nice little link, and you can go to town, have a blast. If you need to know more about theory of statistics, like, I'm here for you. I can support that strange need to know. Okay. And then I leave you a note that if you really want to know how to test for equal variance, like with code, you can use something called a Welch t-test, and like, or ignore the equal variance. Don't worry about that yet. Let's learn how to do a t-test. Here we go. A basic t-test in R. Here's the one piece of code so far that I need you to remember. We're going to run a t-test, okay? The function that we use is t.test. Wow, surprising. And we're testing miles per gallon versus cylinder. Is there a difference between miles per gallon and cylinder? Let's take a look at what the, oh, I didn't plot it. I am just the absolute worst. Does anybody remember how many cylinders we had in our cars? Like, what was the maximum cylinder number?
6, 4.
Yeah, we had like 4, 6, and 8 maybe. So the average of cylinders would then basically be 6, we would assume. Some really low number. How many cars do you think have 6 miles per gallon? Most cars have considerably more than that, right? So just like based on what we know about the data, the average of miles per gallon should be like different than the average of cylinder, yeah? So when we run this t-test, which is the assumption that the t-test makes is like, there's no difference between my two values. Do we think our p-value will be significant in this case? Yeah, hopefully you're nodding your head yes, right? Because we think there's going to be a difference between our two groups. And our t-test is starting with an assumption that there isn't. So if we have a significant p-value, that means that there is in fact a difference. So if we run this t-test, all it's saying is run a t-test of these two groups. You could, if you wanted, just run that, and that is fine. You can just run that. And it hates me. I don't know what I did wrong, but it's fine. We are adding an alternative hypothesis of two-sided, which is just, it'll tell me which one's lower and which one's higher when I enter that. And variance.equal equals false is if our variances are not likely to be equal. So we're kind of able to skirt our assumption. So we'll just go ahead and do that. Error in blah, 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 blah. This works for you if you type it. It's not working for me. But I learned on Tuesday that it worked for everybody else in class. Yes, Andrew.
It is not working for me either.
Not me.
Not working for me.
Neat. Remember when this worked on Tuesday? I do.
Did the Shapiro thing work for anyone else too? Because I didn't really get that either.
Yeah.
When I tried the second Shapiro test, it didn't work.
Same.
Let me figure that out real quick. So the one for cylinder didn't work? Oh, this is an easy fix. All right. Because I haven't reloaded my R, we have always made cylinder into a factor. You remember when we were making plots, we were making cylinder into a factor? You can't do math on letters. So let's change empty cars cylinder back to a number. This is actually an important concept that we need to talk about anyway. So there we go. Now it's back to a number. Our t-test works. Everything is fine. All right. This is what happens when you use the same example data every time and you mess with it in between. So let's talk just quickly about this idea of factors versus numbers, because this is important for all of the homework that you're doing. We have in the past put the thing on our x-axis as a factor. no matter what. And that's because when we graph based on cylinder number, cylinder is a number when it comes into R, and R thinks of it as a number, right? Which makes our axis continuous, which makes all of the colors in our graph blue. To make the colors multiple different colors, we change it to a factor, which basically means that there are going to be many values of y for every value of x, which allows us to color by group. And this is probably confusing some folks, but as a general rule, don't make anything a factor until after you make your first plot and the colors look bad, okay? Don't just default make things into factors, because in your tide pools homework or in your tide pools assignment, I'm asking you to graph on the x and on the y numbers. We want to see the like mathematical relationship between a number and another number on the x and y variables. So if you make one of them into a factor, it's going to mess up everything. So for the tide pools paper and in general, the best practice is don't just default make stuff factors. Make everything into a number, plot it, and if it looks weird, then you change one to a factor. Does that make sense? I know that's a little bit out there. Feel free to hang around for a bit after, and I can show you what that looks like and why that's important. But I'm going to keep going with stats because that's where we're supposed to be. So hopefully that fixed your problem. It should have fixed your problem. And we ran our t-test under the assumption that there is no difference between miles per gallon and cylinder. So let's see what happened. We get this little printout. It says we ran a 2-sample t-test. It gives us a p-value, and that p-value is 15 zeros, 0.15 zeros, and 2. So yeah, that's a significant difference between our two groups, okay? So that p-value tells us there is in fact a difference between the mean of miles per gallon and the mean of cylinder. So which one is greater, miles per gallon or cylinder? And conveniently, it tells us the mean of x, which was miles per gallon, the first one we had, is 20. The mean of y, which was cylinder, is only 2. So there's a difference between the two, and in fact, miles per gallon is higher. Does everybody see how I got that information? Okay. You now understand the t-test. That is it. I gave you some more information about how to do t-tests in here if you want to check it out, but none of it is really that important. This single line of code, that's what I want you to know. Cool? Cool. Thanks for doing things to confirm that you're here and listening. All right. So I gave you a lot of examples, and I gave you some additional wording you're welcome to read. But at the end of the day, you know how to do a t-test, and that works for me. Remember that a t-test can only be used for the difference between one group and another group. And that is like really not very helpful, admittedly. Most of the time in ecology and in life, we want to know the difference between a bunch of stuff all at once, because that's just faster and easier and more interesting. So we need something called an analysis of variance, or an ANOVA. This is the single most common statistical test in academic science. Everybody uses it pretty much, except for like really advanced, fancy, smart, mathy people, which is what I aspire to be, even though I'm terrible at math. It's a simple test, and it allows us to assess the difference between multiple groups at once. And the analysis of variance compares two things. It looks at the difference between groups. So here I have this nice little plot. I've got group blue, group yellow, and group gray, or left, middle, and right if you're colorblind, in which case I hope these colors look different to you, which they should. I think they're colorblind friendly. But anyway, we're looking at the difference between the means. So you can see that the mean has been marked by a dotted line. We're comparing the between group variation. So that's the difference between the means. But we're also comparing the within group variation. And that's the variability within each of these little parabolas, right? So that means we're comparing the mean and the distribution of data. So the mean and the error bars, if you will, of all of our groups, okay? That's how ANOVA works. So on the left, panel A, that is just the between group variation. And on the right, the within group variation is also known as residual variance. And statistical people always talk about residuals, and this is what they mean. It's the variability within a group. Does this matter for you understanding how to make a p-value come out of an ANOVA? No. Maybe it's helpful, though, to think about the idea of statistics if you ever see this again. Okay. The overall summary here is that we care about the variation between the averages and the variation within a group. And that ANOVA relies on something called an F statistic, which is calculated as the variance between groups, which is what you see in A, divided by the variance within groups, which is what you see in B. So if you ever want to do it by hand, you can. It just takes forever. You have to do long division like 4 times. I don't even remember how to do long division because calculators exist and phones and computers and Google. Like, why would I ever do long division? Okay, so let's get into the heart of ANOVA. ANOVA, just like the t-test, is built on assumption. We're going to look at our data and we are going to make some assumptions because that's apparently human nature. Our assumptions are all going to be wrong almost every time, which again is also human nature. So ANOVA assumes the following 4 things. Number 1, all of our data points are independent observations. We're going to circle back to this in a minute. Number 2, there are no significant outliers. So there's no data points that are like 100,000 miles away from everybody else. If they're there, we just delete them. That one's easy. Number 3, our data are normal, so they follow that bell curve. And number 4, we have something called homogeneity or homogeneity of variance. That just means that the error bars are the same size for every group that we're comparing. So you'll see that number 3 and number 4 are the exact same assumptions in our t-test. So we've simply added 2. One is that no outliers exist, and the next one is that all of our numbers are independent of one another. Does anybody know what independence means in terms of sampling? Like, what's an independent sample?
Like prior data or prior collection hasn't affected any of the now data kind of thing, or
Yeah.
like the data.
That's perfect. Yeah. So whatever I'm collecting, every time I collect a sample unit, whatever I've done in the past is not influencing my sample unit, right? So an example of non-independence would be if I go out with my quadrat along my transect line and I see 4 really interesting looking saplings on my transect, and I put my quadrat on top of those saplings every time. And those are the only 4 saplings on my transect. That is not independent sampling because I'm intentionally selecting something that I think is interesting. I am biasing my data and I'm making them all not independent. I have decided that my data are now dependent upon whether there is a sapling or not. Whereas if I take my transect and I just toss it someplace and then I collect data, that's independent sampling. There's a good chance that you are not independently sampling with your quadrat and transect. It's okay. It's okay. What we would assume is that if we were going to do this experiment in real life with your ecology at home project, we would have you lay like 10 transects and like 20 quadrats per transect, and you'd collect so much data that it wouldn't even matter if you were being independent or not. So just like pretend like we're doing that. It's just independence is like not the biggest deal for this kind of project. But in terms of statistics, it becomes quite important. This is actually the most important assumption of ANOVA. If we have independence breakdown, we actually cannot run an analysis of variance. Just a reminder, nobody checks their assumptions. So people do this all the time without actually being allowed to, and nobody's ever been arrested for it. So like, whatever. Those are the 4 assumptions. There's a bunch of ways to test them. Independence, you have to think about your sample size or your sampling design in your experiment. The other 3 we can test with R. So testing for outliers, we'll just take our data and we'll make a nice little box plot. And if we see dots at the higher or lower ends, those are outliers. So we just go into our data and we delete that row. Easy. We can also do an identify outliers test. with this piece of code right here. So this is just me taking empty cars, grouping it by cylinder, and then calculating outliers. And this nice little test, which is just one line of code, tells me, is there an outlier? True. That means yes, there's an outlier. Is the outlier extreme? If that's true, that means my outlier is over 3 standard deviations away from the mean. Extreme outliers can be removed from data. Regular outliers, just leave them. When in doubt, leave everything. Testing for normality and homogeneity of variance, or homoscedasticity, which they also call it for some reason, is a little bit more complicated. And I'm not going to show you that just yet. I'm going to show you how to do that later. First, why don't we just learn how to run an ANOVA? Because that's really why we're here. So an ANOVA, I showed you what the box plot looks like. We are analyzing in our ANOVA, basically, is there an effective cylinder on miles per gallon? So like, look at the data. You can see that we have 3 different groups. Each one is a different cylinder amount, 4, 6, or 8. Does it look like there's an effective cylinder on miles per gallon? Like, oh, hell yeah, probably. Like, definitely. Yes, there is a difference. There is an effect. Cool. Let's like prove that with math real quick. So the way we run an analysis of variance is we type this single line of code. We type AOV for analysis of variance, open bracket, and then we put in our information. So this little formula at the beginning is the 2 variables that we're testing. So we're testing, is there an effective miles per gallon from our y-axis on cylinder, our x, or sorry, is there an effective cylinder, our x-axis, on our y-axis, miles per gallon. So miles per gallon tilde cylinder is what is the effective cylinder on miles per gallon. And then we tell it what data to use. The data is empty cars. It could be whatever we named our data. In this case, it's empty cars. When we run this little AOV, which I'll just run in code because I know it works. Feel free to run it. When we run it, we see nothing. And the reason we see nothing is because I've named it. So to see the output, we have to type empty AOV. And that's going to tell us a bunch of stuff, but none of it's good stuff. There's no p-value when we type empty AOV, right? You don't see any p-values. This is not what we want. Instead, we want to type summary of empty AOV. This is where the p-value is hiding. So this is really all we need. And now you can see how this works. So there's a bunch of statistical mumbo jumbo in this table, but at the end of the day, we see the effective cylinder, and in that row, we scroll to the end and we see the p, which is this PR greater than f. That's the p-value. We see that that p-value is significant, and that it is like 0.00000000006, which is less than 0.05, which tells us there's a significant effect of cylinder on miles per gallon. So let's look back at our figure. There's a significant effect of cylinder on miles per gallon is what that analysis of variance just showed us. What it didn't show us is exactly what that effect is. So we know that cylinder affects miles per gallon, but we don't know whether 4-cylinder cars have significantly higher miles per gallon than 6-cylinder cars or 8-cylinder cars. We also don't know whether 6-cylinder cars are significantly different from 8-cylinder cars. So if I wanted to know the difference between 4-cylinder and 6-cylinder, I could do a t-test, right? Because that's 2 groups. Or between 4 and 8, I could do a t-test, yeah? So you can see here that I actually need to do like 4 or 5 t-tests all at once. And that is a lot of typing. Luckily, there's a way around it. We can do it all at once. The way that we do that is we run our ANOVA, and then we run something called a Tukey honestly significant difference test. And what this is a whole bunch of t-tests all at once. And hopefully, if you've taken science classes and read papers and stuff, like some of these words are sounding kind of familiar. If not, like, that's okay too. We're going to get you there. A Tukey test. This is the same exact figure, only I made it look pretty because I'm a tryhard. Yeah. Thanks for laughing. This figure shows us that there's an effective miles per gallon on cylinder. We can suspect that there's definitely a significant difference between 4-cylinder and 8-cylinder cars. We don't know about 6. but we ran our test, and this is what we ran, exactly what we ran last time, our AOV. I just named it AOV test because I can't keep anything straight and I'm not consistent. So we ran our AOV, and now, here I'll show you in code. I want to know the difference between all of those different groups. So I ran AOV, I ran summary of AOV, and now I'm going to run Tukey HSD, capital T, capital H, capital S, capital D, Tukey HSD of my AOV, of MT AOV. Oh shoot, I done goofed. Let me figure out what I did. I don't think I ran this. Why you gotta be like that? I spelled it wrong. I didn't spell it wrong. Ha ha. This is gonna be the most annoying. Oh my God. Okay. We have to change cylinder back to a factor for this. Okay.
Why do we have to do that?
Great question. Bad luck, really, to be honest. We changed cylinder to a number because the t-test required us to, because you have to have two numbers to do a t-test. For an analysis of variance, cylinder has to be a grouping variable so that we can test the effect of the three different groupings on the miles per gallon. So I know that that's confusing, but that's how this has to be. So for an analysis of variance, one thing has to be a number and one thing has to be a factor. Pretty much all the time for a one-way analysis of variance. So now that we've done that and we've made cylinder into groups, it will now say, what's the difference? You know, it can still assess cylinder with our analysis of variance, but do the Tukey test, it needs to think of cylinder as a group so that it can attest the effect of each group on each other group. So we can still get our p-value, and now we can do our Tukey test. And what it does is it does a bunch of pairwise comparisons or a bunch of t-tests. Here it has done 3 t-tests. And unfortunately, when I made cylinder back into a number and then back into a factor, it changed 4, 6, and 8 into 1, 2, and 3. So it tested the effect of 2 and 1 on 1, the effect of 3 on 1, and the effect of 3 on 2. So that looks just like this. It tested the effect of this on this, it tested the effect of this on this, and then it tested the effect of this on this. So that's all the different t-tests we can do to see if there's a difference between them. And what comes out is we can just look at our p-values. It gives us the difference between 2 and 1 and the difference between 3 and 1. So 2 minus 1 is -7, which tells us that 2 is lower than 1. 3 minus 1 is -11, which tells us that 3 is lower than 1. 3 minus
Your
2 is...
cycles are different numbers, right?
Yeah, yours should be 4, 6, and 8. Yeah. I broke MT cars. I feel like I've told everybody this now, but I broke it. And maybe I helped you break it in your case, and maybe not. It really depends on who you are.
Mine says 1, 2, and 3 now.
Cool. Yeah. I mean, it just... Maybe we should pick a new data set to play with next time, because we broke this one pretty bad. You can still get the basics, though. So we're testing the effects, the differences between these groups, and we can see that there are value differences. Like this is the difference between the means. And then here's our p-value right here. And you can see that there's a significant difference between group 1 and group 2, which is 4 and 6 cylinders. There's a significant difference between group 3 and group 1, so that's 4 and 8 cylinders. And there's a significant difference, p is less than 0.05, between 2 and 3, which is 6 and 8 cylinders. So that means there's a significant difference between this and these two, and between this and this. So there's
I have a question.
Yes.
Does having a p-value of 0 mean anything in particular?
It just means that the value is so close to 0 that r could not make it a number.
Okay.
I think r can only go to the -16, and once you get below once you get below 0.0000000000001, it just calls it 0. Everybody has a limit. -16, I think, is r's limit. Okay, so we've run a t-test. we've run an ANOVA, and we've run a Tukey significant difference test, which is just a bunch of t-tests all at once. That's all I want you to know. I'm going to quickly show you a couple of things. Number one is that the kind of ANOVA that we ran, where we're comparing one thing to a bunch of groups that are within one variable, that is a one-way t-test because we're taking miles per gallon and we're comparing it, we're considering the effect of cylinder on miles per gallon. One variable, one way. If I wanted to do a two-way t-test, I could in fact add another one to this formula. You'll notice that it's different. It's miles per gallon tilde cylinder times gear. So here I'm testing the effect of cylinder and gear at the same time. And this is where you start to see how valuable ANOVA versus t-test can be. I can do a whole lot more testing of different things with an ANOVA. So this is called an interactive effect, an interactive ANOVA. I'm testing the effect of cylinder on miles per gallon. I'm testing the effect of gear on miles per gallon. And I'm testing the effect of both of them at the same time on miles per gallon. If I wanted to test additively, so just each effect separately, I would do it like this. So that's the way we did it. If I wanted to do the same thing, only remove the interaction and just test the effect of each of those two things, I would use a plus sign. Those are both valid options. You can, in fact, add another variable with another multiplication sign or another plus sign and just keep on going. At some point, that becomes really impossible to understand and completely nonsensical. So just don't go above 2 for now. If you get into a place where you're doing analysis in this class and you don't know how to go beyond this, you know who to talk to. We'll figure it out. But you probably won't get in that situation. So we're not going to talk about it. Okay. Now remember all those model assumptions? Normality and all that other nonsense? It turns out you can use one line of code to get the answer to that too. If you load the performance package using library performance, you can in fact just run check model of your analysis of variance, and it'll spit out a nice figure that shows you all of the assumptions together, and you can test that. So let's do that really quick. We ran MTAOV. So let's check the model for MTAOV, which is the effective cylinder on miles per gallon. So it runs and it gives us the following plots. Note that I typed one simple line of code and it made me some beautiful plots. It's even going to tell me how to read them. So we're testing for normality of our residuals, which is our variance. And it says the dots should be plotted along the line. They're kind of not, but they're kind of not at the same rate. So it looks fine, whatever. This is how kind of you just do the check the boxes to make sure the assumptions are fine. Looking at non-normality of our residuals, we can see that we have a normal distribution, but it's kind of squished. This for me, who cares? Looks great. Here we go. On to the next. Homoscedasticity, or the difference between the variances, or the difference between our error bars. Dots should be spread equally along the horizontal line. We can see that they're kind of not, that this one in the middle is a little bit squishier. Whatever, we have sufficiently large N. Carry on. And then here's another way to look at it, and it looks a little better here. So we can pretty much just say whatever, it's fine. Everything's fine. Our assumptions are met, and we can just carry on with our lives. So instead of having to type a bunch of stuff to check the boxes to check your assumptions, you can just use check model. And the more complicated your model gets, it will add in other assumptions. Check model knows how to check your assumptions even if you don't, and it will tell you how to identify whether you have a problem, because it's really cool like that. This allows me to never have to think about this and still not get yelled at, which is so important. Okay, in summary, today in class, I'm gonna try to type this out for you. Let me type. It doesn't want me to. We have learned the following things. We have learned how to run t.test. We have learned how to run a couple of assumption tests that I'm not even going to write because I don't particularly care if you remember. We learned how to run the analysis of variance. We learned that we needed to type summary name of analysis of variance if we wanted to see our p-value. We also learned that if we wanted to understand the difference between multiple groups, we needed to use a Tukey AOV, or Tukey HSD of our AOV. And lastly, we learned that to check our assumptions, we do check model of our AOV. We learned this today. It is 5 lines of code. And then I talked about a whole bunch of stuff. And like that stuff matters, but at the end of the day, if you can do this, and then you can make it make sense to me, we're cool. If you never run a Shapiro-Wilks test, I'm not going to be mad, and you shouldn't be mad either. To be honest, the first time I ever ran one myself was when I started trying to put this model together to teach you how to do this. That's how little people check their assumptions. Like never in my career have I done it. But you should use check model because it's faster and easier. Okay, we have some time for questions if people have them. And then, you know, as people drop off the call or whatever, I'm happy to switch gears and talk about tide pools or homework 3 or whatever you need. So let's do Q&A. Yeah, Wesley.
When you're making the ANOVA, it doesn't matter whether you put MPG first, doesn't matter the order.
It does. It does. The factor needs to go after the tilde.
Okay.
Yeah, the number needs to go before the tilde.
Thanks, Justin. Bye.
Yep. Thanks, Katie. I guess I forgot to tell you what your homework was. For week 4, there is a homework assignment at the bottom, and it's basically, can you run those 5 lines of code? Pick any data and run those 5 lines of code on it. There's 2 steps. 1, read in data. 2, run those 5 lines of code. I saw that even had a question.
Oh, I was just saying, I was just waving, sorry.
Oh.
But I did have one question actually. I noticed that last week, there were some times where I wanted to refer back to the recording for the RStudio instructions and stuff, and it wasn't uploaded. Do you know when you're typically going to upload these classes?
Yeah, so I upload immediately after class ends, but last week I didn't know anybody was watching them, but I'm glad that you were because that's why I record them.
Right.
Last week it failed.
Oh, okay.
And I didn't realize it until, I don't know, Monday or Tuesday. It's like a big file and sometimes it just doesn't go. But if you see that it's not there, like at later tonight, just let me know and I'll fix it.
Sure.
For you.
Yeah, thank you.
Sure.
I had a specific question about my packages because my RStudio is not letting me download the RStatics. I keep getting an error. So I've just been watching, but I haven't been able to download the package for this.
Okay. So RStatics is just an outlier test. You can do that without RStatics just fine.
Okay. I
Yeah.
don't need it.
You don't really need it. It's a little bit easier than the alternatives, but you don't need it.
Okay. Thank you.
Sure.
Thank you.
Yep. And if people are not working on the tide pools yet, like maybe don't leave and at least get the code that I'm going to put in the chat. Yeah. Figure 3 and figure 4 require some new concepts. Does anybody want to go into a breakout room with Beth? Okay, let me get that going.
Thank you, Justin.
Yeah, thanks. You've all been assigned to breakout rooms already. I find that to be very annoying.